Lesson 1, the kinematics of circular motion. We're going to start off with a question. Is it possible for an object to have a constant speed but still be accelerating? Yes, convince me.
You put like a ball, you get something to spin like around the circle, and you can drop it and be accelerated
I think he's on the right track. I'm not sure I quite agree with Brett's explanation.
I don't understand it. You just got something to keep spinning, and just drop it.
So you're dropping the spinning object?
Is it possible for an object to have a constant speed and yet still be accelerating? I think the key to this is to ask ourselves, what is acceleration? There's a 3-word definition for acceleration. The middle word is in. The first word is change. Okay, change in velocity. So what this question is really saying is, can you have a constant speed yet be changing your velocity? I think that asks, go ahead.
You be changing direction?
Yes! Cool. If my candies weren't so stale, I'd give you one right now. Could you be changing direction? In fact, you want to see a great example? This. If I spin a ball around my head on the end of a string, as long as I'm going at the same speed, let's see, around, 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 around. I'm going pretty close to the same speed. It's taking about the same amount of time to go around each time. I'm traveling at a constant speed, but is the direction of the ball, of the mass, changing? It's accelerating. You know how else I can tell it's accelerating, Emily? I can feel it exerting a force on my hand because my hand is exerting a force on it and forces come in pairs. I can feel it. So can you be traveling at a constant speed and still be accelerating? That's going to be the key concept in this unit. The answer is yes. How? Cole, you are correct. Change in direction. And so you were sort of on the right track, Brett, talking about in a circle. I think the falling thing was unnecessary, because I think if you're falling, you are accelerating and therefore changing speed. So for an object, here's the key idea. For an object moving at a constant speed in a circle, like I just demonstrated by whirling that ball around my head, we're going to give that a name. We're going to call it uniform circular motion. Uniform circular motion means you're going in a circle, but your speed's not changing. Its velocity is changing because its direction is changing. And if its velocity is changing, since acceleration is defined as a change in velocity, it must be accelerating. I don't know if there's an acceleration, there must be a force. This is the most important fact to keep in mind. If you're moving in a circle, you're accelerating. If you're moving in a circle, you're accelerating. Well, that leads us to a question, Nathaniel. And the question is, hey, what direction are we accelerating? To find the direction, we're going to do a vector subtraction. Alejandro, we're going to go V final equals V initial plus AT. We're going to get the A by itself, which would be subtract V initial and divide by change in time. Now, change in time is a scalar. It's not going to change the direction of the acceleration. The direction of the acceleration is going to come from V final minus V initial. That's where the direction of the acceleration comes from. So, let's subtract V final minus V initial. Let's do that on the next page. So I've given you a little picture here. I have V initial, and then like a millionth of a second later, here's V final. By the way, I do need to point out to you, when you are moving in a circle, your speed is 90 degrees to the radius. Don't write that down. Your speed right here is that way. Your speed right here is that way. When I whirl this around my head, okay, if I freeze frame it right here, with this right here, and I were to cut the string, which way would this mass fly? Straight towards Dylan. Because its speed is, here's the fancy word, Brett, tangent to the radius. 90 degrees to the radius. If it was right here when I cut the string, Rob would be ducking. If it was right here when I cut the string, Brett would be ducking. A lot of people think that if it's right here and I cut the string, it's going to fly out that way. No, 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 no. It goes 90 degrees to the radius, which I've tried to show in my little picture here. So, how do we subtract two vectors? We don't. You know what we do instead? So I'm actually going to go V final plus the opposite of V initial. So here's V final. Now V initial is that way. What's the opposite of V initial then? Come on. That way, yes? Okay. So I'm going to add, there's negative V initial. And I hope you can see Graydon. Good gosh. Okay, I'm tired. I hope you can see the resultant. I'm going to lengthen it just so it stands out more because I really want to emphasize the direction. This is the direction of the acceleration. What's the direction of the acceleration? The direction of the acceleration when you're moving in a center is toward the, moving in a circle is toward the center. Toward the center. You're accelerating towards the center. If you're right here, your acceleration is that way, towards the center. That's why earlier someone said, is there vectors? Lots of vectors, but we're going to have to add the directions ourselves, and the direction is going to be toward the middle. Oh, unless you're talking about the speed, then it's 90 degrees to the radius. So we see that an object moving in a circle is accelerating towards the center of the circle. We have a fancy phrase for this. We say that it is center seeking, or the physics term is centripetal, with a P, centripetal. Now, some of you may have heard centrifugal with an F. That's bad physics. People talk about centrifugal force because they think that when you're moving in a circle, there's a force pushing you outwards, because they've been on an amusement park ride before that's moved in a circle, and they've said, I'm getting pressed against the door, there must be a force pushing me against the door. No, 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 that's not a force. That's your own mass, that's your inertia, wanting to keep going in a straight line. Centrifugal force is not a legitimate force in our physics world. Centripetal force is the force that's pushing you towards the center. Example 3. A ball on a frictionless tabletop is rolled along a circular track as seen below in top view. The track is not a complete circle, and the ball soon leaves the track. What path does the ball follow after leaving the track? Path A, due to the fact that the ball has circular momentum, which keeps it moving in a circular path for a while after it leaves the track. Path B, since when there is no force on the track, the object would go in a straight line, Newton's first. Or path C, since when the track is no longer supplying a force on the ball will fly outwards. And convince me. Anyone think they know?
This is just a guess, but A, because the acceleration also goes in the middle.
So Cole says, just a guess, A, because the acceleration wants to go to the middle. Can someone convince me that he's wrong or convince me that he's right? Yeah. So right here, it's traveling in that direction, tangent to the radius. No. Once it leaves the track, are there any new forces acting on it anymore? Then I think Newton's first is going to kick in. Newton's first says it wants to keep going in a straight line at a constant speed. In fact, let me refute your argument in a more obvious way. If A was right, if I cut the string, this would keep spinning in a circle. Right? Right? Because if the track is gone, you're saying it keeps remove the track, say string instead. So I think A is wrong. Good guess? I'm glad you did, because it created good discussion. B. All right. Mr. Duick. So, why is it that the acceleration is inwards when the push that we experience in the car seems to be outwards? Now, I've gone on my big rant before. I've said that our bodies are backwards accelerometers, and so, Gianluca, if you're ever in doubt, ask yourself, which way do I feel like I'm being pushed? I'm accelerating in the opposite direction, trust me. That's my fallback. So if you feel like you're getting pushed outwards, you are being pushed inwards, but let's try and convince ourselves why that's the case. When you're turning in a car, friction acts on the car, and it turns the car, but your body, your head, wants to keep going in a straight line. Something has to exert a force on it in order to turn it. The side, if you're in the right-hand side, if you're in the passenger side of your car, the door does. The door pushes against your shoulder. The seatbelt also tugs on you. You feel like you're getting pushed against the door. Actually, no. The door is pushing against you to push you into a circle. The net force is towards the center. Trust me, it is. This is important because many years of experience in a car or on rides lead most students to believe that there is an outwards force. There isn't. There's even a term called centrifugal force, which refers to this apparent outwards push. Not. In fact, there's even machines called centrifuges, which use this force. No, they don't. They use the object's own inertia. So, a bird's eye view confirms that the outwards push is not outwards, straight line, and not a force, but merely inertia. Let me convince you of that. Example 4. If fighter pilots move too fast into a loop, they can become unconscious due to a lack of blood flow to the brain. This is sometimes attributed to centrifugal force. What's really happening? Well, here's our loop. Yep. It's going to look like this. So here's our airplane following a loop. And forget the plane. Here's the pilot sitting in his chair right there. Okay? Your blood is liquid. It can slosh around to a degree. So we're going to look at one huge blood cell. Let's put one big blood cell in the middle of his body, just right around where his heart is, right there. And right now, it's traveling in that direction. And Newton's first law says, Emily, it wants to keep going in a straight line at a constant speed. And because it's liquid and can slosh around, when he gets to here in the loop, where is that blood cell now? In his feet. Now, we say the blood got forced to his feet. That's not what happened. His body got forced away from the blood. But the net result is he's got less blood in his brain. The blood pools up in his feet. He's going to black out. In fact, if you ever watch pilots, if you ever watch the Red Bull speed piloting thing that they have sometimes on like Speed Network or ESPN, and they have a camera focusing on the pilot, you'll see when they're doing a loop, they're gritting their whole face, they're tightening their body. What you're doing is you're using the same muscles you use to try and make your face go red on purpose. You tense your core, you tense your legs, you're trying to constrict the blood vessels, you're trying to keep as much blood as you can in your head. In fact, fighter pilots, jet pilots wear G-suits, and what the G-suit has is cuffs right here, here, and here, and there's an accelerometer in the suit so that when the acceleration, when the G forces, G acceleration, goes beyond a certain amount, these cuffs inflate, and what it does is basically prevents blood from flowing into your legs. Otherwise, this can happen. So, next page. How can we calculate circular acceleration? There is a lovely proof, and Vlad, I'd love to run with it. It's long. I'm just going to give it to you. Here is your equation number 1 for this unit. What does A stand for? Acceleration. What we're going to do is we're going to add a subscript to really focus on the fact that it's circular acceleration. So I'm going to call this AC. Now, normally I'd put a vector sign on there. No, because the direction is going to just be towards the center, we're going to add the direction after the fact, because towards the center, Rob, it depends on where you are in the circle. I'm not ever going to say north or south or east or west. It's towards the middle. And it's calculated v squared over r, where v is the speed that you are moving in a circle, your circular speed, your centripetal speed. And r is the radius, the distance from the circle. Okay, Mr. Dewick, I got the radius, okay. How do you find the circular speed? How do you find v? Oh, great question. Well, v has, since science 10, been distance over time. Meters per second, see it? When we're moving in a circle, then, circular or centripetal speed, and I'm often going to say centripetal velocity, but I mean speed. That's going to be the distance to go around a circle once. We have a fancy name for the distance around a circle once. The circumference. What is the equation for the circumference of a circle? Does anybody remember? It is on your formula sheet, but it's sometimes you haven't memorized. It's not pi r squared, that's the area. 2 pi r. Distance, see it? Over, and the time to go around once, we call that the period. We use a capital T for that. We kind of snuck that into you guys in Physics 11 a little bit. This equation here is not on your formula sheet, but I just showed you how you can derive it. It's distance over time in disguise. You want the centripetal speed? It's 2 pi r over t. Hey, you want to know how fast the Earth is traveling around the sun? It's 2 times pi times the radius of the Earth's orbit around the sun divided by 365 days times 24 hours times 60 minutes times 60 seconds, whatever the heck that is, because I got to go to seconds. That's how fast the Earth is moving around the sun. Hey, you want to know how fast you're moving if you're on the equator of the Earth? It's 2 times pi times the radius of the Earth divided by 24 hours times 60 minutes times 60 seconds. We're not moving at the same speed because we're on the 49th, roughly the 49th parallel. Our radius of rotation is a little bit smaller. Whatever. Concept closely related to period is the frequency. We define the frequency as the number of cycles per second. Period is the number of seconds for one cycle. Frequency is the number of cycles for 1 second. Cycles per second is also called a hertz. So whenever we talk about bandwidth for Wi-Fi and radio waves and things, they're talking about a frequency because they're giving you an answer in megahertz or gigahertz or whatever. If we examine the units for period and frequency, frequency is cycles per second, period is seconds per cycle. We see that they're inverses of each other. For what it's worth, period is 1 divided by the frequency, or frequency is 1 divided by the period. If I know one, I know both. What's the period of the Earth's spin? Well, 24 times 60 times 60. It rotates every 86,400 seconds. What's its frequency in hertz? That. Pretty small. Example 6. Turn the page. An object is moving at 4 meters per second in uniform circular motion. I underlined that for a reason, because this is a trick question. It accelerates at 2 meters per second squared for 3 seconds. Find A, v final, and B, the distance traveled. The trick question is A. V final is 4.0 meters per second. Now, Mr. Dewick, that's V initial, and I see an acceleration and a time. Mr. Dewick, shouldn't I go V initial plus AT. No. What did I underline, Seb? Uniform circular motion. If you're moving in uniform circular motion, you know what you know about your speed? It's constant. But there's an acceleration, Mr. Duke. Yeah, that's the circular acceleration toward the center. It's not the acceleration of the object speeding up or slowing down. B says, how far have you traveled? Well, distance equals VT. Circular distance is going to be circular speed times time. What's the circular speed? 4. What's the time? 3. You know what? You've traveled 12 meters in a circle. What's your displacement? Who cares? It's your distance. You've traveled 12 meters in a circle. So how do we calculate circular or centripetal acceleration? V squared over R. Actually, I don't use that equation that much. There is a second equation for circular acceleration, and it comes from the fact that we said that circular speed was 2 pi r over the period, and that this first equation has a v in it. I can plug that in. I can say, well, 2 pi r over t all squared divided by r. There's v squared over r. Nico, what's 2 squared? And then pi squared, I'm just going to write as pi squared. And then there's an r squared over a t squared. And there's another r on the bottom there. See it, Shashan? Oh, how many r's are there on top? See them? 2? How many on the bottom? Oh, well, one of the r's will cancel as well. This gives us our second equation for centripetal acceleration. 4 pi squared r over t squared. And Brett, you'll notice both are on your formula sheet under the circular motion gravitation unit. Which one do I use, Mr. Duke? Oh, if I know how long it took to go around once, the period, I'll use this one. If I know the speed, I'll use the first one. When you go to Playland, when you're analyzing rides, you probably won't know the speed of the ride moving in a circle, but you will be able to time how long it takes to go around in a circle. You'll end up using this one more often than not. When we're talking about planets, we don't know how fast the planets are traveling, but we do know how long it takes them to go around the sun. We know the period. We use this one more often than not. So, 2 definitions for circular or centripetal acceleration. V squared over r, or 4 pi squared r over t squared, where t is the period. Let's change colors, Mr. Duke. Is right. Where t is the period, r is the radius, and v is the circular speed, where that's 2 pi r over t. So in uniform circular motion, we have a very strange situation. We're moving at a constant speed, but we're accelerating because the direction Cole pointed out is changing. And not only is the direction changing, your acceleration vector direction is changing because it's always towards the center of the circle, which means when you're right here, that's your direction. When you're right here, that's the direction. When you're right here, that's the direction. When you're right here, that's the direction. Your net acceleration, and Emily, therefore your net force, always towards the center. Always towards the center. What that means is we can't use our constant acceleration equations. We can't use these guys anymore. We have to use our new acceleration equation. Question? Get it later. I'll put it back up later. They're right down here, by the way, too. Our new accelerations equation, our new circular velocity equation, circular speed equation. Oh, and distance is still v times t, and v average times change in t if I want to go all funky for displacement. Homework. Now, on your formula sheet, this is the unit where you're going to start using the other page of your formula sheet, the data page. On your formula sheet, I have mass of the Earth, radius of the Earth, period of the Earth's rotation in orbit around the Sun, radius of the Earth's orbit around the Sun, mass of the Sun, mass of the Moon, radius of the Earth's orbit around, or the Moon's orbit around the Earth. I have everything on there somewhere. You have to go hunting for it, but it is there. So what can you do for your homework? You can do number 1, number 2, number 3, number 4, and 5. 1, 2, 3, 4, 5. Skip 6, skip 7, 8, and 9. So 1, 2, 3, 4, 5, 8, and 9. Got some physics toys to show you here.